Okay, let's take a look at section 5.5. This is fun. This is a good section. This is good stuff, and y'all need to be very good at this also, of course. I'm really zoomed in tight. Okay, section 5.5, indefinite, bunch of I's, indefinite integrals. And the big thing, the substitution rule. The substitution rule. That's what we're focused on, is the substitution rule. And this is something you will use. This is a Titution. We will use this a lot. And it's really, once you get comfortable with it, it's really quite fun. Okay, once you get good. Now, this book has a beautiful introduction on page 368 that I would like to read. It's really good. Where am I getting these page numbers? You know what? It does not have a good introduction. It was another book I was looking at. That's terrible. It was a different textbook, so scratch that. I'll have to bring the other textbook and read it because it is really well written. Well, that's frustrating. Okay, so here's something else they talk about. And, you know, all of a sudden they bring this back up, and we know this. But it says again, it goes back to how to integrate all of a sudden back in here. It reminds us how to do this. It's as if we don't know it, or it's as if we weren't supposed to be doing this. But when you integrate a power function or something to a power, like x to the 5th power or something, then when you do this, we know this, you increase your exponent by 1 and you divide. And if you have what we call an indefinite integral, means you don't have an upper or lower limit, that's when you must have the plus constant on the end. So an indefinite integral means that you do not have an upper and lower limit. So if you're not bounded, you don't have an interval for which you're integrating, you come up really with a family of functions by adding a constant to the result. So you must add a constant if you don't have an upper and lower limit. Now, to actually integrate by substitution, the only way I can really show this to you is just to jump in and do it. Okay, just to kind of watch it and get the feel. And then you'll start to kind of get the processing once you've seen it. When you start integrating stuff that you're thinking, I don't know how to do that, stuff like the square root of 1 plus y squared, 2y dy, they want you to be able to integrate that. We do not have the skills to do this. We've never done anything like this. But anytime you have a radical, in general, you're going to probably give a shot to the method of substitution using the information under the radical. What we do when we use the method of substitution is we introduce a new variable, and it's consistently across our textbooks as using the variable u. And it says let u equal the information under the radical. Let u equal 1 plus y squared. Then you take the derivative of u. So if you take du dy, because this new equation is using the y variable, then this equals 2y, which just happens to be also part of our integrand. Then if you actually solve this for du, du equals 2y dy. Now, what you've accomplished here is you've incorporated this part of your integrand by du and this part by u. So what we do in the method of substitution now, this thing is focusing and refocusing, is with this becomes now in terms of u, the square root of u, because u is the 1 plus y squared, and the 2y dy is du. So using the method of substitution, we integrate using an additional variable u, such that we can now do this quite easily. So now this is just the integral of u to the 1/2 du. So now by our integration formula up here, you simply increase the exponent by 1. 1/2 plus 1 is 1/2 plus 2/2, which is 3/2, and divide by that number. And remember, this is an indefinite integral, so you must add a constant to this. You do not have a number for the upper and lower limits. So then this equals 2/3 u to the 3/2 power plus c. But remember, the question was given in the y variable, so you must return it to the y variable as an answer. So now you substitute back into the u that it equals 1 plus y squared. So this is 1 plus y squared to the 3/2 power, and now you have integrated by using what we call the method of substitution, and it is very common to use the variable u. Yes, yeah, sort of. Well, maybe. Having to really stretch that one. First it sounded good, but the more I thought about it, it's like, oh, that's really stretching it. Okay, let's try it again. Suppose we're integrating the square root of 4t, that's the variable t, minus 1 dt. Again, when you're using the method of substitution, you usually let the radicand, the information under the radical, you usually set that equal to u. So we come over here, we introduce this new variable, and we say let u equal 4t minus 1. Then you say, take the derivative. Well, du with respect to t is just 4. Now, I have so far the square root of u, but I've got to get rid of the dt. So now I say du equals 4 dt. Solve it for the du variable, or the du, the derivative with respect to u. Now, I just have dt. I don't have 4 dt. So I've got to solve this for dt. So I'm going to say 1/4 of du equals dt. So now I have the 4t minus 1 replaced by u, and all of dt replaced by 1/4 du. So now everything goes into the variable u. So this is the square root of u times dt is now 1/4 du. And it's okay if you have a constant like 1/4, because you can just pull it into the coefficient of the entire integral. And now you're ready to integrate quite easily. See how simple that becomes? That's pretty neat. So now this is 1/4. This is u to the 1/2. So this is going to be 2/3 u to the 3/2 plus c, which is 1/4 times 2/3 is going to be 1/6 u to the 3/2 power plus c. And then you have to remember, the question was given in the variable t. I must return to the variable t. So, yeah, 1/4 times c is still just an arbitrary constant. So then 4t plus 1 comes back in here, replacing the u variable that we threw into the picture using the method of substitution to come up with the value of the integral. You will get very comfortable with this pretty quickly, and they'll give you plenty of examples to work with because they want you very good at this process. Now let's try another one. Suppose we have the integral of cosine of 7 theta plus 5 d theta. Now, we've never had the argument of a trig function quite that complex. So the argument is the problem. That's a cosine. That's an O. So I'm going to let u be the argument of the trig function, be 7 theta plus 5. Then du d theta, because you're taking the derivative with respect to theta, is 7. Or du equals 7 d theta. Okay, well, I've got the argument replaced, so this would say cosine u. The d theta has to go. So if I solve this for d theta, it's 1/7 du equals d theta. So I can replace the d theta with 1/7 du. So this now, changing it into the variable u, becomes the indefinite integral of cosine of u, and replace the d theta by 1/7 du. So when you integrate, it's the opposite of differentiating, so the integral of cosine u is sine u. Uh-oh, the 1/7 goes in the front, right? 1/7 sine u plus c. But you must go back into the variable of theta, so this is 1/7 sine of 7 theta plus 5 plus c. I pulled that 1/7 out front. I didn't show that step, but I pulled that constant of 1/7 out front of the integral. Okay, this next one's a little bit different. So two of the different parts of substitution is to let u be the radicand under the radical and let u be the argument of a trig function. This one's a little different. Suppose you have x squared sine of x cubed dx. Well, in this case, again, you're going to look at that argument of that trig function and say, man, I hope this works. So you're doing a little bit of guess here, okay? You're just going to kind of give it a shot. So if I come over here and let's just see if it'll work, if I let u continue to be the argument of the trig function, which is x cubed, then du dx would be 3x squared. Hey, this looks good, because in this case, you've replaced the x cubed with u, so you have sine u, and then the rest of this you've got to work with is an x squared dx, and you have an x squared. So this looks like it's going to work. Okay, you have an x squared dx that you're trying to replace with u information, and here's an x squared so far. So this is du equaling 3x squared dx. You just want x squared dx to do this direct substitution. So I'm going to multiply or divide both sides by 1/3. Then I have my x squared dx replaced in terms of u. So this now becomes the integral of sine of u, because x cubed is u, and then the x squared dx is replaced by 1/3 du. Now pull the 1/3 out front, the step I accidentally skipped in the example 3 above. And then the integral of sine u is just cosine u. And don't forget the plus c, because these are indefinite integrals. Hold on, I think you're right. I was thinking of the one above. It is a negative cosine. It is a negative, yeah. So then this answer is a negative 1/3. Replace that u, go back into the x variable, x cubed plus c. It's hard to imagine that we could integrate this pretty complex function that simply. Okay, let's try another one. This just takes a lot of practice. Suppose you're integrating 1 over cosine squared 2x dx. Oh my, cosine squared. No, we don't know how to integrate 1 over cosine squared u even, right? So the cosine squared business isn't good. Do we know how to take the integral of anything that's squared? There you go. We know how to integrate the secant squared. We know this one. Oh, put it under the camera, that would help. Okay. We know that if we integrate secant squared u, it equals tan u. Right? If we integrate secant squared u, it equals tan u. And cosine squared in the denominator is secant. So this is the same thing as secant squared 2x dx. So I can integrate secant squared u, so I got to lose the 2x. So let's let u equal 2x, then du dx equals 2, or du equals 2 dx. Well, we're not quite far enough here. We have now secant squared u, but the dx is going to be replaced. So I need dx, not 2 dx. So I do 1/2 du is dx. So dx will be replaced by 1/2 du, and the 2x will be replaced by u. So now this becomes the integral of secant squared u. This is really not focusing well. Secant squared u, and then dx is replaced by 1/2 du. Or in other words, this is 1/2 the integral of secant squared u du. And now we got it made, because the integral of secant squared u is tan u. So this is 1/2 tangent u plus c. We've integrated. Now we've got to get this variable back to x. So replace that u with 2x, and you have integrated. A pretty complex trig function. By the method of substitution. Okay, and this next one is not a trig function, it's just a bunch of algebra. Looks terrible. Suppose you integrate 2x dx over the cube root of x squared plus 1. 2x dx over the cube root of x squared plus 1. What do you think you should let u equal? Okay. Is it going to work? Okay, take the derivative. Du dx will be 2x. That's looking good. So du would be 2x dx, which is good because that's exactly what you need to let go of is the 2x dx. You got the cube root of u, and you got the 2x dx covered. So this becomes 1 over the cube root of u, and 2x dx is du. That's a very difficult looking function to try to integrate, and it's going to integrate quite easily. So this is u to the negative 1/3 du. So when you add 1 to negative 1/3, it's 2/3. So this becomes 3/2 u to the 2/3 plus your arbitrary constant because it's an indefinite integral. And you have to get all this back into the variable x. So this is 3/2 u we defined as x squared plus 1. And there is the answer to your integration. Pretty nifty. Okay. Now there are a couple of formulas now that we're going to need, and that's they should be on this card also, but I'm going to show you briefly. I hope they're on the little card I gave you. Oh my. I don't see them on the little card. Huh. All right. Well, what's this part D? special formulas, 2 of them. If you want to integrate sine squared x, this is not so easy a thing to do, okay? When you integrate this, by formula, this is x over 2 minus sine 2x over 4 plus c. This is a formula you might want to put on your lovely little card. I cannot believe it's not on there. Now, how did they get that? How did they come up with that formula? What they did was they said one of your identities in trig is that sine squared x is the same as 1 minus cosine 2x over 2, which is 1/2 minus 1/2 cosine 2x. So if you integrate sine squared x, it's the same as integrating 1/2 minus 1/2 cosine 2x dx. And you can use the method of substitution to integrate the cosine 2x. So that's how they did it. And it's not that complex, but you got to either memorize your identity for your trig function or memorize your integral formula. The other formula is if you integrate cosine squared x dx, then it will equal x halves plus sine 2x over 4 plus c. So here's your 2 formulas, and the way it was derived is the same thing. They used that similar identity in which they said, don't forget you have this identity that cosine squared x is 1 plus cosine 2x over 2, and then you could use a method of substitution to integrate that double angle. Okay, so once you get those 2 down, once you've learned those 2 and learned them well, then you go into some examples of applying them. Yes, I'm going to have to write those on my little card. So now, if they ask you to integrate from 0 to 2 pi of sine squared x, then you know by the formula that this is x over 2 minus sine of 2x over 4, and since this is a definite integral, you're not putting a plus c because you're going to evaluate it from 0 to 2 pi. Now remember, they're just asking you to integrate. They're not asking you for area under the curve. So you're not concerned about where it's above the x-axis or below the x-axis. You don't care if this answer is negative or zeroes out. You're just integrating. You're just doing the algebra. So now if I use the upper bound of 2 pi, this is 2 pi over 2 minus sine of 4 pi over 4. That would be your f, your antiderivative of the upper limit, minus f of a, which would be to plug in the 0. So it would be 0 halves minus sine of 0 over 4. Not as many details as we saw in some of those examples we were doing in the last section. It's not going to take a whole page to evaluate this. So this is equal to pi minus sine of 4 pi is like sine of 0, which is just 0. So this is pi minus 0 minus, this is 0. Sine of 0 is 0. Well, isn't this fun? So the answer is just pi. So you can see sometimes when you integrate these definite integrals, they're nice and easy, and other times, oh my gosh, you know, they take a page of numbers, little bitty numbers being subtracted and cubed and everything else. Just takes a lot of accuracy. Okay, let's try another one. Suppose they ask me to integrate 1 over x squared. This one's kind of ugly. Not too bad. Cosine, that's a cosine. Got a little sloppy. Cosine squared of 1 over x. Ooh, dx. Oh boy. This doesn't look like it is exactly fun. Okay, we got a formula for the integral of cosine squared of x. This 1 over x business is not good. Okay, and guess what? On this one, they do give you a hint. And they might give you some hints on some of the harder ones. But the hint is to let u equal a negative 1 over x. Okay, let's see if it works. Surely it's going to work. Okay, well that's the same thing as the negative x to the negative 1. Don't we love all these negative symbols everywhere? So then du dx would be positive 1x to the negative 2 power, which is 1 over x squared. Hey, that's pretty cool. That works. That's a good thing, because here's this 1 over x squared that we got to get rid of. We get a cosine squared u. We got to get rid of the 1 over x squared business. So then we get du equals 1 over x squared dx. Hey, this is nice. That was a good hint. That was a handy little hint. That is nice. So this becomes cosine squared u, and these two guys, 1 over x squared dx, is du. So this becomes cosine squared u du. And we were told that the integral of cosine squared u, oh dear, it's not on my card. I have to go back to my formula, is equal to x halves, which is u now. It's going to equal u halves plus sine 2u over 4 plus c. And remember, your answer, it was given, your variable was x. You have to return to x. And we say u is a negative 1 over x. So this is a negative 1 over x over 2 plus sine of 2 times a negative 1 over x all over 4 plus c. Which equals a negative 1 over 2x plus sine, there's not a whole lot we can do to this, a negative 2 over x divided by 4 plus c. I guess you could say a sine, what's that identity? A sine of a negative x is the same as negative sine of x, right? You remember that? In trig, sine of a negative x is a negative sine of x, right? So this could be rewritten as a negative 1 over 2x minus sine of 2 over x over 4 plus c. That looks a little bit better. Not really, but... Y'all remember that identity? Sort of, maybe? I think I may have seen that at some point in my life. Okay. One more question. It's going to get a new title. F. Initial value examples. This is not hard. It's just the notation. It's kind of wild. Okay, here's what it says. Given ds dt equals 12t times 3t squared minus 1 cubed. And that s of 1 equals 3. The question is, find s of t. Okay, ds dt is like s prime, so I want the antiderivative of ds dt to get s. It's got a plus c on it though. So I'm going to take the antiderivative of ds dt to get s. So I'm going to integrate the 12, okay, s of t will equal the antiderivative of ds dt, which is because ds dt is the first derivative. So I've got to integrate 12t, 3t squared minus 1 cubed dt. I've got to integrate that, and it's going to have a plus c on it. Okay, so to integrate this, what should I let u equal? Yeah, this ugly thing that's being cubed, let's give it a shot there. Okay, let's guess it as being that ugly binomial getting cubed. So let's let it be 3t squared minus 1. Then du dt will equal 6t. Oh man, we're close to the 12t. We're close. Du will equal 6t dt. Okay, this is taken care of by u. This will be u cubed. It's a done deal. It's good. But we have a 12t dt, not a 6t dt. There you go. So if I multiply both sides by 2, then 2 du would cover the 12t dt. So this becomes the integral of u cubed, and the 12t dt is replaced by 2 du. And it's commonplace to rewrite this by pulling that constant out front, in the front of the integral, just as we did it in front of the summation symbol. So this then equals 2 times the integral of u cubed is 1/4 u to the 4th plus c. So this is 1/2 u to the 4th plus c. But I need to get back into the variable t. So this is 1/2 3t squared minus 1 plus c. So this is my s of t function. Now, they gave me some initial value information though. They said that s of 1 equaled 3. Why do they want to tell me that? So what equals? Yes. Why do I do that? There you go. Use to find c. Use to find the arbitrary function. So this means that 3 equals 1/2. 3 times replace t with 1. Replace s of t with 3 and t with 1. This is the ordered pair 1, 3. So 3 becomes 1/2 times 3 minus 1, which is 2. Or 3 equals 1 plus c. Or c equals 2 or 2 equals c. Did I miss a major power? Oh, I did. Did I? I missed like a serious exponent right there. A big old exponent. Man, that is like way off. Okay, so this is supposed to be a 4 right here. So this is supposed to be an 8. And this should be a big old -5. So now the grand answer is that s of t equals 1/2 3t squared minus 1 to the 4th power minus 5. And we are good. We are smart. We know what we are doing. So Integration by substitution is kind of fun. Every now and then it's a little hairy and it's frustrating. It doesn't work like you want it to work and you got to really play with it. But in general, it should work out pretty nicely now, and of course over time the problems will get a little harder. But it's something you need to know and need to be good at. So you guys have some homework today. We covered 2 sections. Go in there in my math. Well, actually don't go right now because I don't even have it set up. But I will go and I will write your homework.